Hey everyone, my name is Jeffrey,
And I'm Ashwarya.
and um, today we are hosting the SSC Exam 1 for Chem 1311 review. Couple of things. This session will be recorded and will consist of a lecture and breakout rooms with practice problems. For those of you who can't make it or have to leave in between, they will be posted on the SSC student website. And if you have any questions for those of you in the live session, feel free to type in the chat and someone will get back to you on that. Without further ado, let's go ahead and get started. So first, we're going to go over CHEM Chapter 1. These are some preliminary things that you should have kind of been familiar with in your high school class or previous chemistry course. But for exam, we're going to touch on some really important topics that are good for this exam, but also good for your future career in this class as well. So we're going to get it started. So dimensional analysis is a really big factor no matter what science you do. Usually, you're going to see this all the time in different ways in your chemistry class, but also some other class like physics as well. So the goal of dimensional analysis is to convert one quantity to another, and we do this by using conversion factors, which is an expression that relates one quantity to its equivalent to another quantity. The way you do this is that you line the conversion factors up so that the numerator and denominator unit cancel each other out. A really simple example I like to use is how many eggs are in 2 dozen? Well, we can say 24, but how do we get 24? Well, we have the known quantity, right, which is 2 dozen. So let's go ahead and say that. So let's go ahead and write 2 dozen. And we need to relate dozen to eggs. And well, how do you do that exactly? So our end product is eggs, so we can go ahead and write that. And the conversion factor that relates eggs in dozens is 1 dozen is equal to 12 eggs. What we do, so the way we round up is that we just go ahead and start multiplying, right? Because now we need to cancel out dozen to get eggs. And how do we do that, we may ask? Well, think back to your math class. Usually when you take a math class, you have to cancel things out. Like the numerator and the denominator each cancel each other out. What's going to happen is that when we put dozen down here, and then we're going to put 12 eggs on here. And how does this give eggs? Well, when this happens, dozen at the bottom, you take 2 times 12, which is 24 eggs. So now if we want to go the reverse way, let's do this example instead of the one down here. So let's say we want to take 24 eggs and we want it to turn into a dozen. Well, how do we do that? So what we do is we say dozen here. And so we use the same conversion factor, but instead of putting dozen at the bottom this time, we want to actually put eggs at the bottom. Let's spell that right. So we put eggs down here, and what happens is that when we do the math, the eggs cancel out. So we put 12 eggs here, we put 1 dozen here. And so what happens is that, like the previous example, we cancel out eggs, and then we'll get 24 divided by 12, or times 1 over 12, which gives you 2 dozen. Yeah, so this seems kind of silly, but this is kind of the basis on what you kind of want to do. So whenever you're doing a dimensional analysis problem, kind of remember like what unit you want and what unit you need to cancel out. A good application here would be your metric units. Usually you want to know these two because they won't give you a chart or anything like that. You have to know these prefixes like how much kilo, how much is hecto, and how much is deca. Will be also useful in other science classes as well. And I know physics does a lot of this with their units. But the principle is you use dimensional analysis to interconvert them. How do we read this graph? So when you see the prefix, right, notice the prefix, and then it's equal to the order of the magnitude. For instance, if I say 1 giga, let's say 1 giga watt, for example. If we have 1 gigawatt, that would equal to 10 to the power 9 of watts. Or, you know, it could also be something else like that. Then we get giga, and we get the order of magnitude here. So the question is, how many kilometers are in 3 meters? So we would use conversion factors here, but a good testing tip is just writing out what you have and what you need. So we have 3 meters here. And then we have, we need to find kilometers. So let's write that. So how do we do this? Well, let's first start off with the conversion factor, right? So how do we read this chap? So I'm going to go ahead and go to my table, find kilo. So it's right there. So we can say that 1 kilo, the unit here is length or meters. And what we're going to do is that you're going to turn this into another quantity. And so because of the table, we can say that it's 10 to the power 3 meters. What is our next step, you might ask? Well, it's time to do dimensional analysis. So when we want to do this example, we want to cancel out meters, right, to get kilometers. So we put meters at the bottom. So we have that quantity. And then we put kilometers on the top. What's going to happen is meters cancels meters. And then we get, so 3 divided by 10 to the power 3 is just -3. So we just say this is our answer. Okay, now let's move on to the next topic. Now we're going to talk about significant figures. So when you're in a lab, we each get like varying data, you know. So it's real important that everyone has like a standard of what to report your numbers in. And so the system of significant figures is kind of what we use to make sure everyone has like the same or relatively the same amount of numbers. And it gives you that precision that you need. So let's go over kind of the basic rules of a sig fig, of these sig figs. So any digit that is not 0 is significant usually. So for instance, 112 has 3 sig figs. Let's see, 1120 would just have 3 sig figs. So sandwich zeros, or I like to call them zeros in between like significant digits, are significant. So in this example, we have 11001. So this is significant. This is significant. These two zeros are significant because they're in between significant digits, and this one is significant. So therefore, it has 5 sig figs. Zeros to the right of the last non-zero digit are significant if there is a decimal point before it. For instance, this number right here, it would have 110. This is significant. This is significant. This is significant, and these two are as well because there's a 0. So it has 5 sig figs. So leading zeros are not significant. So any number that's leading with a 0, essentially. So notice how these 3, they're leading this 4. It only has 1 sig fig. The last rule to keep in mind is zeros to the right of the last non-zero digit and a number that does not contain a decimal point may or may not be significant. Add a decimal to be certain. So for instance, when we have 110, some people may say that it has 2 sig figs or 3 sig figs. It's going to be like a lot of debate. But however, 110 dot has 3. So when we're doing calculations in lab or in your practice, in your problems, you want to like record them to the right sig figs and using these rules. So for multiplication division, the answer must have the same number of significant figures as the measurement with the fewest number of significant figures. For addition or subtraction, the answer must have the same number of decimal points with the measurement that has the fewest decimal places. So for addition and subtraction, you would look for the fewest decimal space, and then for multiplication and division, you would look for the one of the fewest number of sig figs. Sometimes they may be the same thing, but other times they're not. So just go by these rules. For mixed operations, you apply the rules in order. And what I mean is, you just do them in the order you do like this. So for instance, let's go ahead and do this example problem together. So if I take these two numbers, first we want to do in parentheses, right? So I'm going to go ahead and plug that into my calculator. And then I get 69.84. This is my calc, right? Calculator. Now, when I want to, my rules of subtraction says that I have to keep the same decimal, so keep the same number of decimal points with the fewest decimals, right? So we're going to do it based on that one. So we do 69.8 because we just want one decimal point. Okay, so now I'm going to go ahead and do the next part in like, let's say another color, which is like maroon. So we have this number times that number. So I'm going to go ahead and do the same thing. Take this number, 669.8 times 43.3213. And so when I get that answer, we get 3023.83. So we're kind of at a dilemma here. We want our answer to have 1, 2, 3 sig figs, but we have, how do we condense this number? Well, we can return to that problem after we talk about scientific notation. So scientific notation is in this format where you have a number a, where a is between 1 and 10, and it's always to the power of base 10, and n is always an integer. The way to turn numbers into scientific notation is to follow these rules. So for instance, this problem here, you would move the decimal to the left. So we know that there's a decimal spot here, right? So we want it to have a base that's between 1 and 10. So we use 1, 2, 3. And so when you move the decimal to the left, it will be a positive integer. Now, if you wanted to, let's say we have another case, right? So in this case, we have a smaller number, right? So we want to move this decimal, 1, 2, to get a base in between a, and to get a base in between 1 and 10, sorry. And then what do you do that? It's going to be a negative integer. And so here are some other example problems too. But let's go back and return to this one. So let's go ahead, and so we're looking for 3 sig figs because the rule of multiplication applies here, even though we did both multiplication and addition. And so let's kind of think about how we're going to approach this. This is our decimal point, so let's go ahead and move it. 1, 2, 3. Because we moved it to the left, we are going to have to make this base positive. So we jumped how many times? 1, 2, 3. And so this would be our answer here. And I forgot to mention that the number of times you make this jump to get to that base of between 1 and 10 for your a value is just going to be that number that goes on this exponent, on this base 10. Okay, so that will be the end of the review for chapter 1. Now we're going to switch gears and we're going to talk about chapter 2, or atoms and the periodic table. So the discovery of the atom is created by different people. I'm going to go ahead and cover some of the big people here. So first, Thomson, he is credited with the discovery of the charge to the massive ratio of the electron. So he essentially said that the electron is the thing. And he also came up with the splitting model where electrons are dispersed in an atom. His experiment is the cathode ray experiment. So the cathode rays were attracted to, when he shot cathode rays, which are like the form of electrons, were attracted to positively charged plates. So according to opposites attract, so negative charges attract positive and positive attracts negative. Therefore, he rationalized that the cathode rays, or the electrons, must be negative. Millikan discovered the charge and the mass of the electron separately. And what he did was that he suspended oil drops and used math to determine the charge and mass of the electron. Rutherford said that the nucleus had a positive charge in an atom, and he disproved of Thomson's Plum model. How did he do this, you might ask? Well, he's very famous for his gold foil experiment, and what this experiment said that where he shot these particles called the alpha particles, which are positive, deflected or ricocheted off of different angles on a gold foil sheet. So if Thomson's model was true, then it would have just gone through like the atom, right? Because they're just randomly dispersed, so there's no spacing there. However, he realized that it's not the case, and there's actually something there, and that something must be a positively charged nucleus because there was the ricocheting and that deflection. Finally, Chadwick discovered the neutrons, which carry parts of the atom's weight. He did this by emitting radiation, charged radiation or neutrons, by bombarding beryllium atoms with alpha particles. So now we're going to move on and talk about the specific types of atomic particles. So usually you'll see this representation of this atomic particles. We have this AZX format, where X is the chemical symbol of the element, A is the mass number, which is A equals Z, which is Z is the atomic number, or the number of protons, plus N. And N is your neutron number. So let's go over these different types of particles. So the proton is located in the nucleus. It's positive and it has one AMU. How to find? You just look at the periodic table of the element. The way I like to remember is that P is for positive, so just think about that. Neutrons are also in the nucleus. It's also one AMU, and the charge is neutral. And how do we find this? We take the A number and we just minus Z. How do you know this? Well, just like take this number and just take this formula and just solve for Z. Solve for N, and then you just get A minus Z is equal to N. Okay. Next we have the electron, and this time it's different because it's the electron cloud. Now, the mass is negligible, so most of the atom's mass is due to its proton and the neutron, and the charge of it this time is actually going to be negative. How do we find this? We look at the atomic number, and the atomic number is also on your periodic table. So notice how the proton and the electron, like they're the same, but the neutrons differ. And what do we call atoms that have different neutrons, but same protons and electrons? They're called isotopes. So here are some examples. They have the same number of protons and electrons, but they differ in the neutrons. And here are the three. Here's some examples. These are all isotopes of the element hydrogen. There's protium, which has one neutron. Deuterium, it also has. It has zero. Protium has 0 neutrons. Excuse me. Deuterium has 1. How do I know this? I just took 2 minus 1, gave me 1. Tritium has 3, and it has 3. It has this value of 3 minus 1 gives you 2 neutrons. To calculate, usually in experimental data, to find an atomic mass of an element, you'll give like percent abundance of isotopes, and you'll also be given the atomic mass of the isotopes. And what you do is that you just multiply them together and you add them all, and you repeat that for each isotope. Because what an atomic mass is just the average of all known values of the isotopes known for that element. So not necessarily that every piece of like that element has atomic mass. Rather, it's just the sum of the known isotopes, right? So we're gonna move and change gears, and we're gonna talk about the atomic mass mole atom conversion. So what this means is that you can think of a mole as a measurement unit, where a mole of something has 6.022 times 10 to the power 23 atoms, which is known as Avogadro's number. And so it's related by these integer conversions. And how do you convert them? Well, you do that dimensional analysis we were talking about earlier, where if we have grams, right? If we have grams and we divide by molar mass, we're going to get the mole, because what's going to happen is those grams are going to cancel out with other grams and leave you mole. So if we want to go from moles to atoms, we take mole, like this really good example here, it will cancel out, multiply by Avogadro's number, because you're trying to cancel out mole, and to get atoms, you get that value. And if you want to go the different direction, you just do the opposite. So for instance, atoms to moles, instead of multiplying, you just times by the reciprocal or divide by Avogadro's number, and moles to grams, you just multiply by the molar mass. And we'll be having some example problems on this, so keep a lookout on that. Now we're going to talk about the quantum theory and the electronic view of the atom. So this chapter opens up with a relationship between energy and light. So if you remember the colors of the rainbow or GBIF, here kind of like the different types of radiation here. Something I wanted to point out is that the inverse relationship between energy and frequency. So notice how on this side, on the left side, if you have the lower energy and frequency, you have the longest wavelength. On the opposite side, you have the highest energy frequency, but the shorter wavelength. So frequency is defined as how many times a wave passes through a point, and that kind of makes sense here, because you know how if I go from this point and I keep going and I keep going, notice that the distance the distance between it stops. So therefore, the frequency increases because of the shorter wavelength. Something else you can derive: wavelength and frequency are related by this equation. So c is equal to the speed of light. Don't use this number. You can just use 3, which is okay. And c is equal to wavelength times the wavelength equals frequency. So let's talk about the Bohr model. So here is a Bohr model of the atom, and what Bohr basically said was that the electron just like rotates around the element in like a circular orbit. It's also mentioned in quantized level, so meaning that each energy level has their own like energy, but they can't be in what's it called, decimal numbers. So it always has to be 1, it always has to be 2, it always has to be 3. We have a different model. We have the quantum mechanical model, and the quantum mechanical model gives the 3D shape of an element or an atom. So notice here that there's, unlike this one, unlike the past one, notice how this is 2D, but this one is 3D. So we have this, we have more orbitals, we have different n levels, and that stuff. So why did we adopt? So which model do we adopt and why? So we usually adopt the quantum model, and this is because the Bohr model had a lot of issues with it. So the issues it had is that it was based off hydrogen, or it only had 1 proton. So it says that there was a fixed orbit around the nucleus, and they have, which is true, and discrete energy levels in quantum, and that's correct. However, the problem. So we know that it violates the Heisenberg uncertainty principle. We either know, which states that we either know the velocity or the position of the electron at one time, not both. But with this Bohr model, we knew both. It did not account for the 3D shape of the atom. Like I mentioned earlier, the shape of the Bohr model was 2-dimensional, but the quantum model, you saw the different orbitals in it. So that's a difference too. And not all atoms have 1 proton. In fact, only one element has 1 proton, and that's hydrogen. So those are some shortcomings of it, and these were all addressed in the quantum model. So we still kept that at discrete energy levels in quantum, but however, we either know the position or the velocity of the electron at a given time. We account for its 3D shape, and it accounts for multiple protons. So here's kind of a compare contrast between the different models of atoms that we've talked about today. Dalton's here is the Thomson-Pohnpeining model, the Rutherford model, and the Bohr model that we talked about. So we can relate this energy. Before we talk about this, we can talk about like absorbing and emitting energy. So with the existence of quanta means that something can happen when either something jumps from a high level to a lower level of an orbit, or we can have the reverse happen. So let's go through what that means is actually. So right here, I've drawn these models, and this is the nucleus, and there are these energy levels around it. We have n equals 1, n equals 2, and n equals 3. As you go further out, it takes a higher energy to orbit to occupy that level. And this is because you can think of it as like it's going further out, so it needs more energy to keep track of because it's so far away from the nucleus. So that's one way to remember it. So let's talk about, so if we're going from a low energy orbit to a higher energy orbit, we can't just do that naturally. What we need to do is we have to absorb energy. So we have our initial right here, which I circled right there, and then we go to the final. And to jump from a lower level to a higher level, you need to absorb energy. On the other hand, if I start from a higher one to a lower one, you're not gonna need to occupy that energy, all that energy anymore, because you're going to from something that's higher to lower, right? So you need to emit energy. So we'll talk about this more, but right here, if the change in E is greater than 0, that means you absorbed. That means your final level is going to be higher than your initial level, but your delta E is less than 0, you emit something, or your initial is greater than your NF, your final state. So this is not possible by the photoelectric effect. Is when light hits a metal, energy is excited. And so we can actually quantize this, or express this energy as in math. So we have these equations. We have E is the photon energy, H is the Planck constant, and C is this speed of light. Lambda is your photon wavelength, and V is your photon frequency. So a couple things to keep in mind here is that how do we get from here to here? Well, think about our last equation, right, that one. So essentially, if you solve for v, you just get c over lambda. We just divide that. So what happens here is that you get that, you emit that energy. You can make that derivation. It's important to keep both because sometimes, as you see in our practice problems, you need all these three. And so we know these values occur in discrete numbers or discrete energy transitions, or is that each energy transition emits their own light, as in the atomic spectral lines. You can also calculate right here with this formula. A couple things in mind that this is nf squared minus ni squared. So you can combine all these three, and we'll show you how to do that in our practice problems. And here's just a summary of all the formulas to know. Now I'm going to go ahead and pass it off to Ashwarya so that she can continue the second half.
All right. Hi, everyone. Can you hear me?
Yeah, we can hear you.
Okay, cool. So we're going to move on to quantum numbers. So quantum numbers might seem scary at first, but it's just basically a way of identifying the electrons that are in an atom at any point. It's just a way of categorizing the electrons so that we can know how many are in like a certain orbital, in a certain subshell, etc. So the types of quantum numbers that we have are, the first one is our principal quantum number, which is signified by n, and that tells you the orbital level or the energy level. So the possible values for n is anything greater or equal to 1. And then we move on to our angular quantum number, which we denote by the letter L, and that tells us the shape of the orbitals and the number of subshells. So if we move on to the right here, it's just a little table showing the different types of quantum numbers. And so it goes from 0 to 3. And the number L of L tells you what kind of shell it is. So if it's 0, then it's an S and the shape is a sphere. If it's 1, it's P and it's the shape of a dumbbell, so forth. So 2D, 3F, so forth. And then moving on, magnetic quantum number is denoted by ML, and that tells you the orientation of the electron and the number of orbitals in a subshell. And that number can have a possible value of negative L, 0 to positive L. So for example, let's say that our L number was 2. In that case, our ML possible values would be negative 2, negative 1, 0, 1, 2. And then finally, we have our spin quantum number, which is the direction of spin. And there are only two values for that. It can be positive 1/2 and negative 1/2. And what that basically means is that in each little orbital, or like a little dash, when we talk about electron configuration, the electron can be spinning upwards or it can be spinning downwards. And that's what the spin quantum number is referring to. So moving on, this is just another table that shows the different subshells like SPDF, the max amount of orbitals that can be in them, which is always the formula 2L plus 1. So like 0, 2 times 0 plus 1 is 1, 2 times 1 is plus 1 is 3, so forth. And then the values of ML range from like 0 to all the way to like plus minus 3. Okay, so moving forward, we are going to talk about chapter 4, which is the periodic trends of elements. So here we have the periodic table, and the way that this periodic table is structured is that it's showing the different orbitals that each element has. So let's say hydrogen is in the 1s orbital, and so is helium. Helium is also in the 1s orbital. So on this left side, This is the entirety of the s orbital, including helium. And then on the very right side, this is the p orbital, which contains 6 electrons, and the 2 orbital contains up to 2 electrons. And then in the middle, we have our d orbital, which contains up to 10 electrons. And then at the very bottom, we have our f orbital, which contains up to 14 electrons. So atomic orbitals and writing electron configuration. So the way that we write electron configurations is that we're going from like the first row of orbitals to the second row of orbitals, and then we go to the p orbitals on that side, and then we go to 3s, and then we go to 3p. And then we start our d orbital also on the subshell 3. But the thing is that the way it is on the periodic table, it kind of starts one after the s and f orbital, s and p orbitals. So our notation for anything that has a 3d orbitals or is in this like transition metal state would be 4s, and then we go on to write 3d, and then we would write 4p. Let's see, I don't think we have an example right here, but Jeffrey is writing something. So we would have 4s, then 3d, and then 4p. And then I don't think it'll usually happen, but like f orbitals are 2 past like the s and p orbitals. So that would start with our 6s and 6p, and then we would move on to 4f. But we can move on to the next slide. So there are some principles that help us write our electron configurations. The first one is the Aufbau principle, which says that electrons will occupy the lowest energy level orbital that will receive it. So there's no such thing as an electron going straight to the 6s orbital. It'll always start in the 1s orbital if the 1s orbital is open. And next we have our Pauli exclusion principle, which says that no 2 electrons within an atom. Oh, I think you went up a little. Oh, were you trying to show something?
Oh, no, you're good. My apologies. Go.
Yeah. Yeah, so no 2 electrons within an atom may have an identical set of all 4 quantum numbers. So that's why quantum numbers are really important, because they're kind of like a unique code for identifying any particular electron within an atom. So you can't have 2 electrons with the same set of quantum numbers in any case. And then Hund's rule states that electrons will occupy all empty orbitals in a subshell with single electrons having parallel spins before entering half-filled orbitals. So what this means is that in 2p, if we have 3 electrons, it's not like the electron will go down and then go up again. The 3 electrons will all spin upwards because they want to fill all the empty orbitals within the subshell before they start pairing up with each other. And so since it's chemistry, there's always got to be exceptions to something that we learned. So in our electron configuration exceptions, we have some elements, some rows in the periodic table where the electron configuration isn't necessarily what we would expect. So we have our tables over here, which are the elements copper, silver, and gold. And it's saying our predicted electron configuration for those would be, like for copper in particular, it'd be noble gas configuration AR 3D9 4S2. But the actual electron configuration is AR 3D10 4S1. And that is because a full orbital is much more stable than an unfilled orbital. And a half-filled orbital is much more stable than a partially filled orbital. So in order to either completely fill its orbitals or partially like half fill their orbitals, the element will take an orbital from a higher shell and move it down to its lower shells in order to satisfy that. So As you can see, it moves it from its 4s to the 3d orbital just to fill it so it can be more stable. And so another type of elements that also have those like unique exceptions are chromium and molybdenum, which take one electron from their s orbitals to half fill their d orbitals. So I would know those exceptions very well because they always ask questions about them. All right, and so now moving on, we're going to the electron configuration of ions. So ions are basically charged atoms. So a neutral atom, when it loses its electrons, it becomes more positive, which means it, and we call those cations. But when a neutral atom gains electrons, we call those anions. And so on the right side here, we have just a little guide on how to write the electron configuration of an ion. So you want to write the original configuration that that atom would have if it was neutral. And then you go look to see the charge of it. So if it's +2, that means you have to remove 2 electrons from its highest shell. So the example here is that we have Na, and we're trying to write the electron configuration for Na+, which means that it lost 1 electron. So originally the highest subshell was 3s1, but it loses that 1 electron from the s orbital when it becomes an ion, which means that all that's remaining is 1s2, 2s2, and 2p6. And that would be 10 electrons total instead of its normal 11. And then on the other hand, Cl is gaining 1 electron. So it is normally it's 1s2, 2s2, 2p6, 3s2, 3p5, but since it gains another electron, we add that to its highest orbital shell, which is the p3p. And so now everything is filled out in the 3p orbital. So it's 1s2, 2s2, 2p6, 3s2, and 3p6. And so now we're moving on to talk about effective nuclear charge, which is the net positive charge that is experienced by an outer shell electron in an atom, or we can also call outer shell electrons valence electrons for atoms. So our example here is sodium, and sodium has 10 inner electrons and 11 protons, and it has 1 valence electron on its outside. So now we're trying to figure out what charge does that nucleus exert on that 1 valence electron. And so we use this formula, which is Z effective is equal to Z, which is the charge of the nucleus, the number of protons, minus the core inner electrons, which are shielding those valence electrons. So you can use the number of electrons in the noble gas that preceded that element. That's like the most used. The best bet is to use like the number of electrons in the previous noble gas for that. So in that, for that one, oh, it's neon, right? Is the next one? I think it's neon, but so we have 11 and then we subtract 10 electrons. And so the Z effective would be +1. And so that 1 valence electron in sodium has a Z effective of +1. So we're going to just briefly cover some periodic trends, which are atomic radius, which is defined as the total distance from an atom's nucleus to the outermost orbital of an electron. We can move on. And so here is like a visual representation of the atomic radius across the periodic table. And the atomic radius increases as you go down a group, but decreases as you go across a period. So it goes it increases as you go from top to bottom, but it decreases as you go from left to right. And the reason why it increases when you're going from top to bottom is because the shells are increasing in the atoms. And the reason why it's decreasing as you go from left to right is the number of protons that are in the nucleus is increasing. So it's pulling in the electrons more strongly than the atoms on the left side of the periodic table, which have fewer protons. and more electrons in comparison. So we can move on. And then this is just a overview of like the general periodic trends. Ionization energy, electron, like most of these aren't covered on your test, but it's also just good to keep them in mind because it's good to know the periodic trends when you are thinking of general chemistry, when you're just doing general chemistry things. So now we're going to talk about some electron configuration trends. So elements in the same group of the periodic table, which is like 1A, 2A, like 6A, 7A, etc., they'll all have the same number of valence shell electrons, which are their electrons in their highest energy level. So group 7A is known as the halogens, and it includes like fluorine, chlorine, bromine, etc. And all of these elements are going to have 7 periodic tables. Not 7 periodic tables, sorry, 7 valence electrons. And then on the group 1A, which are our alkali metals, all of those are going to have 1 valence electron. And then on group 2A, everyone has 2 valence electrons, so forth. As you go across the periodic table from left to right, the amount of valence electrons in the highest shell increases. And this is just to show you like the amount of electrons in each shell, just like a general overview. So you have your 1s, there's 2 electrons total in that, and you have your 2s, 2 electrons total, 2p6, which is 6 electrons total, so on and so forth. For most of your atoms, you combine the s orbital and the p orbital to determine the total amount of valence electrons. And I believe that's it for the lecture, if I'm not mistaken.
That's correct.
So, yeah, now we're going to take a 5-minute break, right?
Yes.
Yeah, so right now it's 7:47, and so we'll regroup at 7:52, and then we will start our breakout sessions, and we'll go over some practice problems as well.
Okay, everyone. So since it's 52, we're going to go ahead and start the breakout session. So I'm going to go ahead and share my screen. Give me 1 second to do so. Okay, everyone. So we're going to go ahead and start this problem for number 1. So number 1 asked, how many nanometers are in 32 meters? So the way we tackle this problem is that we want to do those dimensional analysis crossroads. What I mean by that is we're going to have to cancel out those meters. So if I take my pen and let's start off with our known. So you always want to write out what you're given and what you want. So you want nanometers, right? And so we need a conversion factor that relates the nanometers to the meters. And a convenient one is that 1 meter is equal to 10 to the power of -9 nanometers. And so when this happens, all we have to do is now multiply and arrange somewhere we need. So we need nanometers, right? So we got to cancel out meters. So when we do that, we write meters at the bottom, we put nanometers there. Now fill in what we know. That's a negative there. This is a 1. And when you do this problem, we get 3.2 times 10 to the power of -8 nanometers. And that will be your answer. Number 1-2. Determine the number of significant figures in each of the following measurements. So let's go ahead and take a look at this. So non-zero numbers are significant. So these are all non-zero. So therefore, 4 significant figures. These zeros are leading zeros, so we don't count them. So therefore, it's just that one significant, which is just 1. And this one, there's 1, 2, 3 significant figures. For sigfigs in scientific notation, you just count those numbers, not the ones on the right. So therefore, that's 3. Any questions so far? If you have the questions, we can continue. So carry out the operations. Round to the appropriate number of significant figures. So I'm going to go ahead and plug this number into our calculator. I get 1484.28. And then we want it, so they're more multiplying, right? I mean, multiply, we just keep it to the least amount of sig figs. So this one has 3. This one has 4. We take the one with 3, and we ignore the one with 4. So to do this, we gotta move this 1, 2, 3. So the reason why we're doing this in scientific notation is that we want it to have 3 sig figs, right? But we can't do that unless we measure the first A base, so like that. And since we move the decimal points 1, 2, 3 times to the left, we'll put a positive 3 up there. The next problem is a multi-step problem. So you want to do the first step first. It's going to be, if you do the first part, you're going to get 31.2 plus 46.32. So when I plug that number into my calculator, I get 78.42 times 5 times 4. So now what you want to do is that you want to do that for the sig fig, right? Correct sig number of sig figs. So it's going to be 78.4 to times 5.4. And why do we chop off the 2? Well, we chopped off the 2 because we wanted to have 3 sig fig. I mean, addition, it's the least number of decimal points, right? So this one is the last decimal point. It's the least. Anywho, I'm doing this next operation, 78.4 times 5.4. I get in my calculator 42.3.6. And when I have to round, we're doing multiplication, right? So this is 2 sig figs, so it's the least. So we round this to 2 sig figs. Turning this into 2 sig figs gives you that for your base in scientific notation. Move 1, 2. And then to move 2 times to the left, we do that, number 2 there. Okay, so the next one is just a subtraction problem. 63.4 minus 32.123. I get, when I put it in my calculator, let's go ahead and box these numbers so that it's easy to follow. We get that number. We do 30. We get this number in the calculator. And what's going to happen is that we round it to 1 decimal point because it's the decimal point that matters when we're doing subtraction or addition. And we get 31.3. Okay. Any questions so far? Okay, sounds good. Any questions? Okay. So express each number in scientific notation. So the decimal point is here. We want to go 1, 2, 3, 4, 5, so that we get an A base between 1 and 10. So we get 3.212334 times 10 to the power of, let's see, how many times did we jump? We jumped 1, 2, 3, 4, 5. We jumped 5. So we put a 5 here. And we put positive 5 because it is we move to the left. So here, we move to the right. So 1, 2, 3, 4. We move that. This is our base. Times 10 to the power of 4, but we make it negative this time. Any questions? No questions, so let's go ahead and move on. Which of the following choices are paired correctly? So Chadwick did come up with the neutron. Rutherford was not the fighting model, however. He was actually the gold. He did the gold experiment. Thomson is wrong. Did not find the neutron. That was Chadwick. Okay, so 22-2 asks, identify the protons, neutrons, and electrons, and the atomic mass for this symbol on to the right. So this number here is our mass number, which is the proton plus neutron. This one is our protons. So therefore we have 6 protons, right? And since we have 6 protons, we have 13 minus 6 neutrons, which is 7, and electrons, they're just the same as the protons, so we have 6. So the next problem, any questions on this one? Okay, no questions, so go ahead and do this. So how many moles are in 32 grams of carbon? We have 32 grams of carbon, right? And so we want to convert them into moles, right? So we need a conversion factor to get moles of carbon. So therefore, we can get something like, so from the periodic table, we have 1 mole of carbon is equal to 12.01 grams, right? So to cancel grams, because we want moles, we put grams at the bottom. We put a 1 mole here. Okay, and so when we do that, we get 2.66 moles. Any questions so far? Questions? Okay, we can keep going. Next question. How many grams are in 3.75 times 10 to the power 26 molecules of iron? So what's going to happen here is we're going to take 3.75 times 10 to the power 26. We're going to need to go from, so our plan is we need to get to atoms, right? I mean, yeah, we need to get the grams. But we started with molecules, okay? So we can't really go directly from molecules to grams. So you remember from that chart, we first have to go from molecules to moles, right? Because that's related by Avogadro's number. And then we go from moles to grams, and that is related by the number of grams on the periodic table. So we have, so molecules, right? This number of molecules times 1 mole over 6.02 times 10 to the power 23 times 55.841, and this is from the periodic table of iron. And so when we do the math, we get 3.48 times 10 to the power 4 grams. Okay, let's move on to the next one. Any questions on this? No questions? Okay. Calculate the wavelength in meters of light that has an energy of 1.32 times 10 to the power negative 23 joules per photon. So the way you want to do this is that you want to find the energy of a proton. So we have that, right? So we know the formula, this one, relates the energy of a proton with the wavelength. I'm sorry, with the frequency. So we have this value, the E, which is that. And then we have Planck's constants, which is 6.62 times 10 to the power of negative 34. And then we don't know what that is for frequency. So when we solve this by dividing, we get frequency is equal to 1.999 times 10 to the power of, where's that? So that's not an E, but that's like base 10. So let me go ahead and write that just to clear. Okay, so we have that. Now we need a formula that will relate the frequency and the wavelength. And we know that from the speed of light, which is the wavelength lambda times this v, which is frequency, we get. So when we plug in our known values, the speed of light is always 10 to the power to 8 equal to, we don't know that, times the value that we just found. Excuse me. We get solving for this, solving for wavelength, we get wavelength equal to 1.50 times 10 to the power of -2. Okay, so that was a bit of a doozy. Does anyone have any questions? Okay. So 3-2, calculate the energy in joules of a photon with wavelength of 5.00 times 10 to the power of 4 nanometers. So let's go ahead and take a look at this problem. We have to take the speed of light. We know we have a wavelength, right? So something that relates wavelength and frequency is this formula right here. So when we plug it in, just for simplicity's sake, the E means to the power of base 10, or in this case, power of base 10. That's a 8, excuse me. Wavelength is 5 times 10 to the 4 nanometers. However, we got to convert that into meters themselves, so we just get a 9 here. And then what we get is, this is a 4, sorry. And then we solve for frequency, we get this value. So how do we find the energy of the proton? We use just this formula right here, the Planck's constant. So E is equal to 6.62 times 10 to the power of -34 times 6 to the power of 12. And plugging that number into your calculator, you get 3.97 times 10 to the power of -21 joules. Go ahead and box that. Okay, so next is a 4-part problem. For an electron that goes from n equals 4 to n equals 2, calculate the energy change that occurs when an electron makes this transition. Okay, so how do we do this? We take delta E is equal to this formula. And then we plug in what we know. So what I like to do on a test is I take this one, I label it an F, and I take this one and I go label it an I, because it's going, this is before, this is after, okay? So what's going to happen is that we just plug in what we know and we chug it in the calculator. Good thing to keep in mind is that you want to square these values before you do them. So it'll be a shame if you got these points wrong because you didn't square them. So let's do it. And then when we get this value, we get delta E is equal to -4.09 times 10 to the power of -9 joules. So what does this value mean? It means that you see this negative right here? That's going to be a indication of when energy is released, because if the change in energy is negative, that means something was released. So would your answer be the same if the electron moved from n equals 2 to n equals 4? The magnitude would be the same, so we can say that the mag is same, the magnitude is same. However, what would not be the same is the sign, because when you're going from a lower level to a higher level, what's going to happen is that you're going to need to absorb energy. So instead of negative, it would be positive. Sine would be positive instead. Okay, so C asks for us to calculate the wavelength that corresponds to this transition. How do we do this? Well, we take this value here, this formula, and then we take this derivation of it, because we know that frequency is just C over wavelength. And once we solve for that value, we can say that delta wavelength is equal to HCE. And so E also corresponds to a energy change. And where do we see this formula? We saw it like up here, right? When we did 3A. So therefore, we can get 6.62 times 10 to the power of negative 34 times 3 to the power of 8, 10 to the power of 8 over negative 4.09 times 10 to the negative 19, I believe is the answer, right? Yeah, okay. Okay, so it will actually be, sorry, not 19, just 9. So when we calculate this number, we're going to get a negative value, which is this value. However, you can't have a negative wavelength, right? So therefore, you just say that, oh, we can have a negative, so it's just the positive value of that, which is the answer. And why did we get a negative? Well, we got a negative because we said that this was an emission, right? So since our magnitude of delta E was negative, calculation-wise, we get a negative value. But conceptually, there's no such thing as a negative wavelength, right? Because you can't be negative, you can have negative length. So therefore, you just take the positive value of that. So that's the answer. Is this an absorption or an emission? This would be an emission because we're going from high energy to low energy level, and we're having negative delta E value instead. Yeah. So this one's a bit of a doozy, so I'll give you all a second to do this one. So I'll give you 1 second to do that. Okay, so let's go ahead and continue this problem. So the easiest way to do this problem is to look at the periodic table. So if you count in all the ranges for n equals 3, you get 18. For this one, you get, for you say when n equals 4, L equals 2, you get 10. For n equals 4, L equals 3, m sub L equals 2, you just get 2 values. And then for D, the only number of these quantum numbers is just 1. So another way you can do this is that you can individually list out the quantum numbers for each, and then find the number of values that are instance. For instance, if you listed all the quantum numbers possible for n equals 3, you'll get 18 possible values all the way to m sub s. Do the same thing for here. You get 10, 2, and 1. So 3-5 says which of these quantum numbers can exist. So let's take a look at this rule. So we have n equals 1, that's greater than 1 or equal to 1. L is equal to 1. That can't exist because L values can only go from 0 to 1. So n minus 1, sorry. So this is 0 to n minus 1. That's 1 itself, so that's wrong. N equals 3, L equals 0, that's correct, because the possible values for L are L is equal to 0, 1, 2. M sub L for an L equals 0 is just going to be 0. That makes sense. So C as n equals 4, L equals 1, that exists. M sub L is just the negative L to the positive L value of L, that makes sense. So that's correct. So D, we have n equals 2, L equals 1, that makes sense. And then M sub L is equal to 2, that can't be it, because for L equals to 1, we get M sub L values of negative 1, 0, 1. So that is wrong. So the correct answer is B and C. Okay, let's move into the next configuration. So, 6 asks, finding the noble gas configuration of the following elements. I guess this would be best split if I go ahead and just share all of my screen so that I can pull out the periodic table. So I'll go ahead and do that. So just give me 1 second. Go ahead and do that. Just 1 second. Go ahead and switch from here to here. Okay, so let's go ahead and continue working on this with our periodic table on the side, so which we can like reference. Okay, so write the noble gas configuration of the following elements. So noble gas configuration is when you just start at the highest, what's it called? The highest noble gas. So if we look at bromine, sorry. So we go Br is right here. We have Ar. So what we do is we do Ar, and then we go from the next block, which is the 4s block. So that's for us, and then we jump down to the 3D block. Remember, we have 3D, and then we have 10. We have to go through all 10 of those electrons to cross back again to the 4p block. And so bromine is the 5th one in line. Okay. Next we have Cu. So that's right here. So just do the same thing. Start with Ar. And then we go from 4s, we start from 4s2. But wait, you might be thinking, oh, we could 4s2. But if we look, copper is one of those exceptions. So instead of the 2, we have to put the 1, and then we do 3d10. This is an exception that you guys need to know. So the next problem is write the electron configuration for the following ions. So F minus is essentially just F with one more electron because it's indicated by the minus. So we just write the normally for F, right? So it's 1s, 2, 2s, 2, and 2p5. But instead of 2p5, we got to add one more because of the anion, which gained a negative charge. So that's 2p6. Calcium 2 plus. It's going to be 1s2, 2s2, 2p6, 3s2, 3p6, and we would normally write 4s2 because it's in this 4s2 block, but we don't do that because we just take 2, so therefore we can just leave that as our answer. Determine the effective nuclear charge for each of the following. So we just apply that formula that we know. So we just take our Z minus S. So our atomic number minus the inner core electrons. So the core for Ne would just be 2. So 10 minus 2, 8, positive 8, Na plus would be 11 minus 2 this time, plus 9. And then we have F minus, which is also 9 minus 2. So So the ionization energies for Mg are as follows. The ionization energies increase with, so we have this here, this here, this here. Explain the following two observations. The ionization energies increase with each successive electron that is lost. So IE3 is much larger than IE2 and IE1. So let's take a look at the first statement. So we can say that with each successive electron lost, the nucleus pulls the remaining electron closer, making it harder to take another one out. So therefore, you need more energy need. For B, your ionization energy after ionization. So for B, after ionization 2, you are trying to remove stable core electrons, which the molecules do not want. So if we take a look at magnesium, right? For magnesium, the first one is a valence electron, so we chop that off. It's good. Na is also this other electron is also going to be the valence electron, and then they have the other one, which is AR, right? But then you pull that one off, and that's a core electron, and we don't want to do that.
Hey.
Hey. Oh, I'm still recording this, by the way.
Oh, right. Sorry.
Yeah, you're good. So therefore, but did you need anything though?
No.
Okay, sounds good. So yeah, that's what you would do for there. Okay, so so next we have trends. So to remind us of the trends, we have in this direction atomic radius increases, and then we have from this direction atomic radius increases. So filling in the chart, the other trends, they go that way. So ionization energy, electron affinity, and then this way for ionization energy, and then electron affinity. And so to sum it up, this is high here, ZF is high, atomic radius is low, this is high, high, this is high, and then this is low, and this is high, and this is low and low. So for this exam, I would focus on ZF and atomic radius, but the other ones will probably be in your other exam. So 4-4, rank the following atomic from the ionic radius. So atoms, sorry. So if we look at the periodic table, since K is like right over here, we can say that that's going to be the largest radius, and then gallium, because if I remember correctly, gallium is right there, right? And then selenium is right there, and then we have Kr, which is that one. So we just do this. So if we're ranking from ionization energy, it's the opposite trend. So atomic radius is always the oddball, so we can say atomic radius, ionization energy, and then it's Kr, Se, Ga, K. And notice how it's just a flip of this too. So atomic radius will always have the oddball out. Okay, so next is this activity. So we just fill in the chart. So this is going to be, so let's go down the road. Number of electrons in the outermost shell. This is just 1, 2, 3, 4, 5, 6, 7, 8. This is going to be number of electrons lost. So the octet rule. So you want -1 for that, -2, -3, -4. But however, on the opposite side, you want to gain 3 instead of losing 5 because that requires less energy to gain 3 rather than lose 5. do +2 +1, and you don't need to gain anything here. And then there's 0. And then there, for the one number of electrons transferred, is just the same thing over here, right? And then for charges to the ions form, it's a -1 because we gain an electron. We gain an negative charge, -2. So this can also be +4, by the way, forgot to mention, because this is a special case, the 4A groups. This is a -3. This is going to be +-4. We have +3, then +2, +1, 0. We have, yeah. So this is going to be metal, metal, metal. So this one can be any of the 3. So metal, non-metal, non-metal, and metalloid. And then we have this ones are usually non-metals, non-metals, because non-metals usually want to gain electrons. And, yeah. And the group no gases are non-metals too. Okay, so let's move on to the next problem. We have how many valence of electrons have, so following the same rule as last time, bromine is in group 7, it's in group 7A. So 7A. AS, arsenic, is 5 in group 5A. So notice how if it's in a group A element, the number of valence electrons matches whatever group it's in. How many valence electrons do the following have? Fluorine is in group 7. Cesium is just 1. Selenium 6, 2. Sister is 2. I is 7. And then P is 5. And you look at this using the periodic table. For each of the following pairs, select the one with the largest radius. So we're going to need our periodic table again for this. So this is going to be, A is going to be CS, right? Because CS and K going down a group, it increases, so therefore CS is the one. P or Cl, so going to the left to the right, it decreases, therefore P has the bigger one. C or BR, BR would have this one because group trends take priority over period trends. And if you think about it, group 7 has 7 rings versus carbon, which only has 4, so the rings are further out. So with these anions, it's going to be different. So with anions, they're usually going to be bigger because what's going to happen is because it gains an electron, the Z effective force is weakened, so you won't have those electrons pulling in as much. So those electrons are going to be free, so Cl minus there. And then Ni plus or Ni2. So with that being said, cations work the opposite. So the more positive something is, the more ZF is going to have, because it's going to have, those protons are going to exhibit more force on those electrons because of the removal of those electrons. So if there are smaller electrons amount and higher and the same amount of protons, what's going to happen is that the same amount of protons are going to exert the same force on the electrons. So it kind of makes sense why the cation is going to be smaller. So Ni is going to be smaller than Ni plus because it's the lower magnitude. Br minus versus rubidium plus. So we're going to have to look at this, right? So let's take Ni plus, right? If I remember correctly, Ni is right there. I mean, sorry, Br minus is krypton, and then Ni2 plus is going to be, so Ni is right there, 1, 2. So it's going to have the same configuration as Fe. So we compare Fe and Kr. So with that being said, usually the anion will have the higher one. So it's Br minus. Okay, so rank the following ions from smallest to largest. We have 36. So the way I would do this is that I would take rank, just write out the number of electrons, right? Okay, so 38, this is 38, this is 20 protons, and this is going to be 36 electrons, and this is going to be 36 electrons. 36 electrons and 36 electrons. Sorry, this is going to be 18, excuse me. 18, and then Rb plus is 37 protons. So how do we do this? So usually the cation's going to have the higher ones. So we can say that let's compare like the anions first. So we have an anion, which is going to be usually the biggest. Then we're going to say krypton because it's the neutral one. Then we compare the cations. So first, let's compare the ones with the same electrons, right? So we have Rb2 plus, and we have Sr2 plus. So what's going to happen is that Rb plus is going to be like that. It's going to be next because it's going to have what's it called? The third most electron shielding, or sorry, not shielding, but the ZF, right? And then it's going to be Sr plus, and then it's going to be Ca2 plus. And that's the end of this packet. Thank you, everyone.